All right, so the first thing we're going to look at is topic 1.4, polynomial functions. So let's look at this graph first. That's a starting point. So we're going to analyze all aspects of this graph. So first, roots. Okay, you see single root, double root, triple root. So roots are basically another way to say zeros, right? So for example, in a graph, x minus 3. Y equals x minus 3. The zero would be at 3 because 3 is what makes this whole function y equals 0. So for example, and it was x minus 3 times x minus 4, then the zeros would be 4 and 3 because either of these would make the function 0 since they multiply each other and 0 times any number is also 0. So when it's just a single root, which means single root means like single, it refers to the power of x. So for example, x to the 1, then it just crosses the x-axis. It's just passing through, right? But then a double root, x plus 1 squared. So since the 0 is at -1, it's x plus 1 and it's squared, which means that it bounces. So you see how if this was just x plus 1, here, zoom in on that squared there, right? If you can see it, here, I'll write it down here too. X plus 1 squared. So that makes it bounce. It's kind of like a quadratic, right? It's just like a normal quadratic in how x bounces. Now, let's look at this third root over here. So x minus 3 squared. So because this is like around where x is 3, do x minus 3, it's cubed, x minus 3 cubed. And whenever the degree is odd, it's going to pass through the axis. And whenever it's even, it's going to bounce or reflect in some way. So 3, it's odd, so it's going to pass through. And what it does, it passes through, but it flattens out before it passes through. So it flattens out and changes concavity. We went over concavity last lesson, and like quick recap on that, concavity is where the rate of change is increasing or the rate of change is decreasing. So if the rate of change is increasing, it's like, okay, it's going like that. And the rate of change is increasing, that's concave up. And then here, the rate of change is, okay, I'm gonna go, yeah, here the rate of change is decreasing. So it's going down, down, it's going down faster. So that's concave down. All right, here, and then now let's look at local maximum and global maximums. So local maximum, right? This is basically where the function is, it has like, it's higher than either of the points around it, right? All of the points, like either of the points around it. So if you take a point to the left of it, right here, it's higher than that. And you take a point to the right of it, right here, it's also higher than that. Like 2 points, very close proximity to it. So that, therefore, that's a local maximum. And at a local maximum, the rate of change is going to be 0. So it's similar to like vertex, where if I were to ask you where the function is increasing, then you would say, let's say I'm just asking you about this portion of the graph from like here and to the left, then you would say from negative infinity, because it's increasing from negative infinity and like that keeps going. And then it stops at the vertex. Let's assume the vertex is like -4. So that's going to be one vertex. That's going to be the vertex, and therefore negative infinity is going to be, sorry, that kind of doesn't really look like infinity. Okay, there. Negative infinity, that's going to be open bracket, and -4, also an open bracket. Open bracket or parentheses makes it so it's not included within our domain. And then here, let me erase this line now. Okay. And then here, this would be a local minimum. It's the same concept where here the point's greater, here the point's greater, so this must be local minimum. And here is not us. Here is a global maximum. Now, all global maximums are also local maximums, but it's not vice versa. It's kind of like a square and rectangle, right? So basically, the global maximum, the left point and right point, it's greater than both, so therefore it's a local maximum. And it's the global maximum because out of all the points in the graph, this right here is the highest point. All right. And then end behavior at large x. So as x approaches infinity, you can see that the function is going down, which means as x approaches infinity, y approaches negative infinity. And we'll go over more on that later. Okay, now let's go down. Okay, so you guys see this graph, and there's a couple questions on this graph. So I'm gonna go over this graph. So we'll work on this one together. You guys can also work individually if you want, and then send the answers in chat or just tell me. And I'm going to be solving it at the same time. So the local extrema, right? Okay, so there seems to be a local extrema here. This looks like a local minimum. Around here is like a local maximum. And around here, another local minimum. And around here, another local maximum. Okay, so there seems to be four local extrema with two of them being minimums. So two min, and then, so that's one, two, and then two maximums. One, two maximums, two max. Okay, so we identified all the local extrema. Now, here's the thing that some people get confused with usually. So the global extrema, right? Now you might be saying, okay, is this point right here a local extrema? And I mean a global extrema, a global minimum. It would be no, it's not the correct. It's not a global extrema because the point here, you can see that the graph is approaching negative infinity as x approaches infinity. So therefore, this is not the global extremum because we don't have a global minimum for this graph because the graph is infinitely going downwards to negative infinity. And over here, it's infinitely going upwards to infinity. So there's also no global maximum. Now, what must happen between each zero? Second question. Between each zero, if you look at a zero here, here, instead of, I'll circle the zeros in different colors so you guys don't get mixed up. Okay, zero, zero, this is also zero, and this is also zero. So do you guys notice a pattern about what's happening between the zeros? The black circles are the local extremas, and the blue circles are the zeros. So between any two zeros, you need to have, and you will have either a local minimum or maximum, right? Because if you just think about it, right, you're going past the zero, so eventually you have to turn back to go back to the x-axis and reach the next zero, which would result in a local minimum here, here a local maximum, and then so on, right? And another pattern is if there's four zeros, four distinct zeros. So for example, distinct zero, right? If x minus 2 squared. This is technically two zeros, two roots, but it's only one distinct zero. On a graph, this would only result in one point where it's actually zero, which is right there. Now, let's take that off. So there's always going to be one less of the extremas than the number of zeros. So for example, here, a number of distinct zeros, that's key. So here there's four distinct zeros, so there's three extrema. And you can do that to check if you're like, when you're looking for extrema, you can always check, do I have one less extrema uh than the zeros? Or actually, no, it can at max be what's it called? It can at max be the number of zeros because here there's actually four extremas because this zero is also an extrema. And wait, there's a question. Is it true that there is one less turning point than the multiplicity of the function. So one less term, let me try. Okay, so you're saying, okay, so multiplicity of a function, let's look at yeah, that's usually true because for example, this would be a function of here. Let's look at x minus 3. And let's just look at an example to answer that. So here's x equals 2. Here's x equals 3. So first of all, it's degree 3. So we're going to start here. And then you go, and then it's a 2, so it bounces. Degree 2, so it bounces. 1 turning point, 2 turning point. Yeah, it's always going to be one less turning point than the multiplicity of a function. You can see that with this example here. And that happens, and if there's one, if the multiplicity is 1, then there would be no turning points. Okay, now let's look at inflection points. So let's just, this is just kind of a review from last lesson. So we're just going to identify the inflection points real quick. So the graph is going down, and then the rate of change, this seems to be concave up for this portion. And suddenly somewhere here, change from concave up to concave down. So I'm going to put it that like there. Sure, we'll say that's the point that's concave down. And then we continue, we continue, we continue. And then somewhere on this portion, it's changing from concave down to concave up. So we'll say that's here. And then we continue. So that's another point of inflection. And then we continue, continue, continue. And somewhere here, it changes back to concave down. So we don't need the exact points, but we can identify that there's 3 points of inflection on this graph. Now, concave up and concave down intervals. So it's going to be concave down from here to here, concave down from here to here, and back to concave up from here to here, and then concave down again from here to here, and it's infinitely concave down after that. Okay, then increasing and decreasing intervals. So this is the last thing we're going to look at on this graph. So the graph, where is it decreasing? Let's look at that first. First of all, let's give a point for these extremists so that we. Oh yeah, good question, Anya. So we won't be able to know exactly where the point of inflection is, and they're not going to ask you in any pre-cal test what's the exact point of inflection. And so therefore, we just kind of have to look kind of around where it looks like the graph is changing from concave up to concave down or vice versa. So over here, it's concave up, right? It's increasing, it's increasing. And then somewhere here, since this portion is concave down, you can see that like it's making like a frown face, so it's concave down. Somewhere here, like somewhere in this area, it's changing from concave up to concave down. So somewhere there's the point of inflection. And as long as you put it somewhere in that region, you'll get the points for it, and no points will be taken off. You can't find exactly where it is. Okay, good question. Now, next. Uh, so increasing, decreasing intervals, right? So yeah, let me give points for all extrema. So this is at x equals -2, x equals 0, x equals 1, and x equals 2. Okay, so first it's decreasing. Let's look at decreasing. It's decreasing from -infinity to -2. And notice how I use parentheses because the local minimum is considered like a vertex point where the rate of change is 0, and it's not decreasing there. So we don't include that, so it's parentheses. And then we put union to indicate there's more in the domain. 0 to 1. Again, notice the parentheses. And then finally, 2 to infinity. Now, this is where it's decreasing. So let's write that. Decreasing. And then let's look at increasing now. It looks like it's increasing from this point to this point. So -2 parentheses to 0 parentheses, and then 1 to 2 also parentheses. All right. Any questions on anything we just went over? I'm going to give you guys some problems for this now. Okay.
Isn't it increasing from negative infinity to -2? Is it not increasing?
From negative infinity to -2.
Yeah, yeah,
No,
it's increasing because
the rate of change is increasing, but the graph itself is decreasing. All right, that's a common misconception. So basically, it's concave up, right? So you can see that the rate
yes.
of change of it is increasing. So like here, let's estimate the rate of change to be around like -1, and then here it's like it's 0 at the vertex, and then here it's probably like 1. So that's
Oh,
we're
okay, we're talking about value. Yes, thank
yeah,
you.
yeah, yeah. We're talking about yeah. So we're talking about the actual values of the graph. Okay, next. Okay, here's 3 questions for you guys and the topics they're testing on. And then just drop your answers either in the chat or just say them verbally. And I'll give you guys like 3 minutes to solve these. And then I'll solve them with you guys. And yeah. Let me give you guys like 1 more minute. All right, I'm gonna go ahead and explain these now. Okay, so first, local minimum changes from decreasing to increasing. So if a degree 4 polynomial has 3 extrema, can it have 4 zeros? So the answer is yes, it can have 4 zeros because for extrema, the condition is if there can only be as much zeros, there has to be at least as much zeros as there are extrema. For example, if there was 5 extrema, then it wouldn't be possible for there to be 4 zeros. But since there's only 3 extrema, it's possible for there to be 4 zeros. Okay, next, inflection point concavity switch. Where does a cubic function, which hasn't been shifted up or down from its parent function, which is just x cubed, shift from concave down to concave up. Okay, let's look at this. X cubed. So where does it switch from concave up to concave down? So let's look at this. So at this point, uh if we look here, it's kind of the rate of change is decreasing. Actually, I kind of drew that bad. Let me try that again. It's, it's more like, yeah. All right. So as you can see, like here, the rate of change kind of seems to be decreasing. It's concave down, and then here it's concave up. And that happens, that change, the inflection point on this graph happens at 0, comma 0, which is its vertex. But if the graph was shifted down, then it would move down along with it. But since they said we can't shift the graph up or down, then where does it switch from concave down to concave up? It's wherever its 0 is. So for example, x minus 3 cubed. Let's look at this graph now. It would be like that's 3. So let's get so something like that. And it's concave down from here to here, and concave up from here to here. And it changes at its 0. So the answer to the second question is it's 0. And then for the third question, do odd degree polynomials have global extrema? And the answer for that question is going to be no. Because if you think about any odd degree polynomial, let's look at just y equals x. So it's going to start at negative infinity and then go to infinity. And the thing about odd degree polynomials is always as x decreases, whether y is going to negative infinity or infinity, when x increases, it's going to do the opposite. So it's going to go to infinity or negative infinity, which is correlated. So look, here y equals x, and if we look at y equals negative x cubed, for example, it's going to be something like this. And as you can see, there can't be any extrema here because it's this is going to infinity and this is going to infinity. So both are covered. Here, let's look at like a kind of different type of graph. So one like this, there would still be no global extrema because it's going to negative infinity over here, infinity over here. So there can't be a global maximum or global minimum. All right, now let's move to the next topic. It's right, yeah, it's right there. Okay, topic 1.5, complex zeros and symmetry. So when a function is odd, it crosses the axis linearly. We went over this, and then when it's even, the graph bounces at the axis, kind of like a quadratic. So like that was the axis. And then when it's odd multiplicity, but the multiplicity is greater than 1, it crosses the axis and flattens out. So kind of like it crosses it, but it flattens out and then crosses it. Okay. Now, let's look at even and odd functions, how to identify them. So even function, I think you're unmuted. Oh, shit. All right.
Oh,
Uh,
sorry.
it's fine. Yeah. For even, f of negative x equals f of x. And for odd, f of negative x equals negative f of x. And we'll look at what that means now. Okay. So here's an even function, x squared. So first, let's look at it graphically. All right. So f of negative x, how's that going to work? Basically, this side, it's a reflection over the x-axis, right? So we're reflecting it over this line. So because of that, this side, let's make to make it easier for you guys to see, I'm gonna make this side red and this side blue. Okay? When we reflect this, it's just going to be like this. So the blue side switch sides and the red side switch sides. But it's still the same graph. It's just a side switch. So it looks the exact same. And now let's look at it algebraically. X squared, right? We have to prove that x squared, since we have to prove that f of negative x equals f of x, we just plug in negative x for every place x is. So negative x squared, well, since we're squaring it, it's just x squared. So it equals x squared. So therefore, these two are equal. So therefore, x squared we've proved is an even function. Now let's look at this. X cubed. This is an odd function. And first of all, since the local extrema are like, I mean, there's one side going to negative infinity and one side going to infinity, you can also see through that. But not all graphs that are going from negative infinity to and then infinity on the other side are odd, and we'll go over that later. Okay. So here again, let's label this as blue and this as red. So for in an odd function, let's go back up. F of negative x must equals negative f of x. So let's write that down here. F of negative x equals negative f of x. Okay, first let's look at that graphically. So if we draw a second graph here and we show, let's first draw negative f of x. That means this side is going to go there, then this side is going to go there. So we're reflecting over the y-axis. So it's going to result in something like that. Now, this is negative f of x, right? Now, let's look at f of negative x. Now this is reflecting over the x-axis, so we're reflecting over this line, which means, let's erase, put that back. So that means we're reflecting like this. So this is going up. No, sorry. It's reflecting like this. So this is going flip into this side, this flipping to that side, which means the red side is gonna be like that, right? Blue side is gonna be like that. So if you look at these two graphs, these two, then you can see they're the same graph. It's just that the sides are that are reflected are different. So we can see that graphically this is an odd function. Now let's prove it algebraically. So x cubed, right? X cubed, f of negative x. When we plug in f of negative x for x cubed, it's going to be negative x cubed. And this just equals negative x cubed, like without the parentheses, right? And the reason for this, whereas like for example, if it equaled negative x squared, then it would just equal positive x squared, right? That's because it's an even function. But odd, for example, how you can think of it is, let's put x as 2. Negative 2 times negative 2 equals 4. This is positive, right? This is negative 2 squared. But if we multiply that by negative 2 again, 4 multiplied by negative 2, that's negative 8. And that time we multiplied negative 2 3 times. So negative 2 times negative 2 times negative 2, which is negative 8. So therefore, this is negative x cubed. Now, if we look at negative x cubed, which is what negative f of x is, that also equals negative x cubed. So therefore, f of negative x, which is negative x cubed, and negative f of x, which is also negative x cubed, are equal. So therefore, we've proved that it's an odd function. Now, Also, any questions on that? I know there's a lot of lines and different stuff on your screen right now. All right, let's move on to a question. So let me erase some of this so that this can see better. Okay, I want you guys to focus on this question right now. Now, is this an even question, an even function? And I want you guys to prove it. And then I'll prove it in like a minute with you guys. Then we have some functions after that. By the way, in around 3 minutes, the meeting's automatically going to end since Zoom has like limits on how long I can present. So just join back after that and I'll create the meeting again. Okay, so f of x equals this, right? So now we have to find what f of negative x is to find if it's even. F of negative x equals, so we're just going to plug in negative x in all the spots we see x. So negative x to the sixth plus 7 times negative x to the fourth plus 3 times negative x squared minus 13. Now, negative x to the sixth, since it's going to an even degree, it's being multiplied by itself an even number of times, which means that is just x to the sixth. And then the second term is just 7x to the fourth. Third term is just 3x squared. And then the final term, we didn't change it at all. It's just negative 13. So f of negative x equals this. X to the sixth plus 7x to the fourth plus 3x squared minus 13. Now, if we look at our original equation, which is f of x, that equals the exact same. So therefore, since these two equal, this is an even function. Even. Now let's look at this one. This. So we have to find if this function is even or odd. So first, when you're testing for even or odd functions, always look at f of negative x first. So since this is f of x, you can see, okay, now f of negative x, let's plug it in. So negative x cubed plus 3 times negative x. So if we multiply this out, this is just going to be negative x cubed minus 3x. Okay, so that is clearly not equal to f of x. So we know this is not an even function. So let's write this down. F of negative x equals negative x cubed minus 3x. Now we have to find what negative f of x is. So to do that, we just multiply all of x cubed plus 3x by a negative 1. So negative x cubed plus 3x. And if we multiply this out using distributed property, it's going to be negative x cubed minus 3x. Therefore, both f of x, negative f of x and f of negative x are equal. So therefore, this is an odd function. Okay, now I want you guys to look at these two th functions before I give you a trick. And I want you to find if they're even, odd, or neither. Okay, so x to the fifth plus x to the fourth plus 3x squared plus 5x plus 4. So first we'll test if this is an even function, checking for f of negative x. And to do this, we plug in negative x in all of the places where there's x. So negative x to the fifth is just negative x to the 5. And then negative x to the fourth is x to the fourth. And then negative x squared is just 3x squared. It's just x squared, so 3x squared. And then the same process, minus 5x plus 4. So we can see that this is not an even function since these two do not equal each other. Now we'll check if it's an odd function, which we do negative f of x. So we just multiply this whole thing by negative. So if we multiply this by negative 1, right? Then we get negative x to the fifth. Okay, so far so good. But we get negative x to the fourth. So that's already wrong, but we'll just continue. Negative x squared, again, not right. Minus 5x minus 4. Okay, so I want you guys to see a pattern here. So this is, first of all, neither. It's not odd nor even, so we can write down neither. I want you guys to notice a pattern here. So a function can only be odd or even if all of their degrees are odd or even. So for example, what that means is here, the degree is 5, and the degree is 1. So there are two odds in here, but then here there's even. And since there's evens, it can't be a odd function or an even function because there's both odds and evens, right? So that's one pattern. Like anytime you see a function where there's both odds and evens, they can't be either odd or even. It's always going to be neither. And here, x cubed plus 7. So first of all, right away we can identify there's no even degrees here. So it can't be an even function, right? But we'll just test it. F of negative x. That's going to be negative x cubed plus 7. And that's because negative x to which we plug in wherever x is cubed is just negative x cubed. Negative x cubed plus 7. Whereas negative f of x is, we multiply this by negative 1. It's going to be negative x cubed minus 7. So these two do not equal each other either. So this is also going to be neither. Now, I want you guys to notice a second pattern here. Neither. Let me erase this negative. Okay, here's a second pattern. Whenever you have a function where there's only odd degrees, you know that it can't be even. But the second thing is if it has like something that's that's not x, for example, just 7 here, right? Or like if it was 4 or 3, it doesn't really matter, right? That it's not going to be a odd function. And the reason for that is if you think about it, the 7 will always become negative 7 when you do negative f of x. Here, negative f of x became negative 7. But when you just do negative x, f of negative x, that's not going to change. It's just going to stay positive 7. So there's no way that the two functions could equal each other. And let's look at that graphically too. So a function is odd the when this quadrant 1, so this quadrant, wait, actually, that's such a bad circle. Okay, so this quadrant and this quadrant are reflections of each other, right? It's like you reflect it and you get the same. But when you shift it And when you do +7, that's shifting it up or down, right? So when you shift it up or down, becomes, for example, +7, it would be like probably like that. Then these two quadrants, they're not similar. Or it could also be these two quadrants, for example, like this quadrant and this quadrant. But yeah, the two quadrants opposite to each other have to be similar, right? And they're not. So therefore, whenever there's a number and it's not x, it's gonna not be an odd function. Okay, next. Fundamental theorem of algebra. Okay, so this is something key. A polynomial of degree n has exactly n complex zeros, including multiplicities. Example, if a degree 5 polynomial has zeros at 2i and 3, which has a multiplicity of 2, what are the other zeros? So first of all, if it has 3 multiplicity 2, that's just x minus 3 squared. And later you'll learn how to like find how to write something for I, but I'll just we'll skip over that for now. But what you need to know is that you get I from taking a square root of a negative number. So I equals square root of -1. And what's one thing about square roots? Square roots always have a positive and a negative. So if you take any square root, it's going to be positive and negative. So, for example, square root of 25 can be either 5 or -5. So there's always two. So here, if you look at 2i, and since you know you get I from taking the square root, another is also there's 2i, and then there's -2i. That's another zero that you have, another complex zero. Now, complex zeros don't actually have to be on your graph. Those are just distinct zeros and root. They're called roots. But this complex zeros, they can be anything. Like I, imaginary numbers. And for the last zero or complex zero, we don't know it. So here's a question for you guys. All zeros of a function that has a degree of 4. You have to find all the zeros of it. And I'm giving you two of the zeros. 3 plus I, and here, let me rewrite this one. Ignore that. It looks bad. Okay, 3 plus I and 4i. What are all the zeros? And I want you to find that. And before we do that, the conjugate, to find the second zero, 2i versus -2i, what you have to do is just wherever the term is I, you have to make it negative. So for example, 1 plus I would become 1 minus I. So that's the pair. 1 plus I and 1 minus I, they're a pair. Okay. And yeah, in the chat, that's correct, Ochud. So what are the conjugate pairs, the two other zeros for 3 plus I and 4i? I'll give you guys like 30 more seconds. All right, I'm gonna go over the answers. So since we're just trying to make I negative, the pair for 3 plus I is going to be 3 minus I, and the pair for 4i is going to be -4i. Now, any questions on that, by the way? All right, none. Okay, that's good. Now let's see. First of all, okay. So last couple things here. So now we're going over limit statements. First of all, let's study what happens in even degree. So for example, even degree and odd degree. So here's an even degree function. For example, x squared. It's just going to be like that, right? So therefore, it's going to infinity on both sides. Whenever x is going to negative infinity, y is going to infinity. And as x is approaching infinity, y is also going to infinity. So the end behavior for this is going to be this right here. You zoom in, x to infinity, f of x, which is y, to infinity, then x to negative infinity, f of x to infinity. Now, excuse me, the we're talking about positive leading coefficient here, right? So it's just x squared. So the leading coefficient is 1, right? Now, what's your leading coefficient? It's going to be the number that goes along with the x of highest degree. For example, in the function 3x cubed plus 2x plus 5, the leading coefficient is going to be 3. Now, here's a quick question for y'all. What's the leading coefficient for this function? And just go ahead and say it out loud or put it in the chat. Yeah, correct. The leading coefficient is going to be 5. And that's because even though at the start is x squared, which would have a leading coefficient of 1, since degree 4 is the highest in this equation, 5 is going to be our leading coefficient. Oh, yeah. So a negative leading coefficient here, x squared has a positive leading coefficient. Let's look at negative x squared. It's going to have a negative leading coefficient, which means that the end behaviors are going to both be negative. So for even functions, all you need to memorize is that uh, whenever the leading coefficient is positive, both sides go to infinity. And whenever it's negative, both sides go to negative infinity. So it's pretty simple, right? But for odds, it's a little different. So if we're looking at odd functions, we'll look on this side. Okay. For odd functions, for example, x cubed. When it's a positive leading coefficient for odd functions, you're going to go to negative infinity on the left side. So when x is going to negative infinity, y is also negative infinity. And when x is going to infinity, y is to infinity as well. But when the leading coefficient is negative, so negative x cubed, then it flips. So as x is going to negative infinity, y will be going to infinity. And as x is going to infinity, y is negative infinity. So any questions on that? All right. So again, x squared, x cubed, those are examples. Oh yeah. So I'll have a question for you guys. On this graph, is A positive or negative? Danya and Pranav, y'all haven't answered anything. Y'all want to go ahead and give this one a try? Give you like 10 more seconds. All right, yeah, that's correct. It is negative. So, uh, A is negative because as you can see, we can identify this is an even function because both sides are going the same way. Whenever both sides are going to, as x goes to negative infinity and x goes to infinity, both extremes are approaching the same y, which is like here in this case, both y's are approaching negative infinity, then it's even. Or if both y's are approaching infinity like that, then it's also even, right? The only case where it's odd is when one is negative infinity and the other is infinity, or vice versa. So therefore, we know it's an even function, and we know that even functions only go to negative infinity when a is negative. So therefore, we found out that the a value for this, the leading coefficient, is negative. Now, let's go over limit statements here. So limit is basically a way of saying, oh yeah, where does y go when x goes to a certain point, a certain like unreachable number. For example, here, as x is approaching negative infinity, f of x is approaching infinity. What that means is that this is just the one for this would be the graph like this. So as x is approaching negative infinity, so x is going that way. Y is going to infinity. Y is like reaching this limitless boundary. It's just going up and up and up. And then as x is going to infinity, the limit of f of x is equals negative infinity. So as x is going that way to infinity boundlessly, this is like going down infinitely to negative infinity. So what is the degree and leading coefficient? I'm going to give you guys a different problem since I showed you that one. What's the degree and leading coefficient? What's the lowest degree and leading coefficient for All right, so what's the lowest degree that's possible for this for using these limit statements? What's the lowest degree graph that's possible? And is the leading coefficient positive or negative? And I'll give you guys a second to answer that. All right, so here's a solution. So limit f of x equals infinity x uh, to negative infinity. Limit f of x equals infinity, x to infinity. So we're trying to find the lowest possible degree and the leading coefficient. So let's draw this out, right, to make it simple. X to infinity as f of x, as x is going to negative infinity, f of x is infinity, so it's like something like that. And then it's same for when f of x equals it. F of x also equals infinity. So as x is going to infinity, f of x is going to infinity, checks out, x is going to infinity, f of x also equals infinity. Okay, so we know that this must be an even function because on both sides, f of x is going to infinity. And since these are both going positively, we know that the leading coefficient is positive. These are going to positive infinity, and it's an even function. And as for the lowest degree, since it must be an even function, the lowest degree even function is a quadratic. So just x squared. So the lowest degree will be 2. All right. Any questions on that or anything we had before this? Let me know. And with that being said, that's going to be it for today.